Hi, welcome. I'm Sean Isom. I'm the CEO and founder of Renderlit.
And I'm Mendy, software engineer at Renderlit.
And today we're going to be talking about how you can make games and any 3D application more powerful in WebAssembly using plugins. Let's get started. OK, so I want to take us through an example of how 3D content is built today in many games. This is kind of an interaction that you see here between a designer on the left and a developer on the right. So let's say you've got a brief that says you need an animated disco ball. OK, so you might want to hook into a game engine, be able to use geometry functions that are explored by that engine, integrate that with the content creation app, and you have a portion of a disco ball. That's great, but that's static content. And so now we need data in order to animate that. Well, where do we get that data? Let's say you want to make a disco ball rotate with the music that you're playing. Well, you might need to plumb through animation parameters through the engine, time or events or something of the like. And so you can see this is becoming increasingly complicated over time. But now, does it look right? No, it looks weird in the game. It looks different in my content creation tool than it does in my actual 3D scene. And you see this look of consternation on the face of the programmer, and now at this point, the artist here. I don't know, try this, I guess. This is just kind of an illustration of how painful it is and how expensive it is to build these kinds of applications today. And here you'll see this is a screenshot from an excellent talk called The Next Leap, How AI Will Change the 3D Industry by Andrew Price. This is a scene from a Tom Clancy video game. And based off of kind of an average hourly rate for a 3D artist of about $40 an hour, you can see how truly expensive the final cost to deliver these kinds of assets into this game are right here. And a lot of that stems from the ability to produce content that works in this game, but that can't necessarily be reused. Like, let's take a look at that truck over there, for example, $5,600. There's shattered glass on the screen of that, which is really cool. But how did that glass shatter? Like maybe a piece of trash fell out of the trash can. You've got a spline that's animating that, and that has some sort of interaction with that glass, and that's all very specific to the scene. But what if you want a general framework for breaking any glass on any window anywhere? And that's because this is hard to do. Content is expensive to build. You can see we're just basically throwing money out the window every time we're trying to rebuild this kind of thing for different games. But the scope, the quality bar of content, the quantity, as consoles get more powerful, as GPUs get more powerful, as we have these more immersive experiences all over the place, this just gets expensive to build over time. And these assets are not reusable. Something I'll call out is, anybody here heard of GLTF? Anybody's done 3D work? So GLTF is very powerful, but it's mostly for static data, right? So it's very good at defining vertex formats, ways to get data onto the GPU. But what about all of the effects? What about the data flow? What about the parameters? Everything around that. We think plugins can help. So rendering should become plugin driven, and we're going to give some great examples of that today. In order to kind of marry the code with the data to produce that kind of 3D scene that you saw there in a reusable way and lower the cost to develop those assets. Let's define a plugin as this: third-party code called over a well-defined interface. This is kind of a broad explanation of a plugin. Everybody might have their own preconceived notion of what a plugin is coming into this talk. But let's go through some examples of some plugins real quick. So quick show of hands. Who here has used Winamp? Yeah, all right. Dating myself a bit, but that's a great example of a plugin, right? You remember those little visualizers in there? You have a frequency coming out for the music. You can write little animations, make some fire maybe, put it into this desktop, but put it into a frame of a known shape and size inside this host app. Let's go a little bit more broad. Photoshop. Any Photoshop users here? Probably a few, yep. Photoshop's great because even if you haven't gone and installed Photoshop plugins, Photoshop is a plugin-based architecture, and much of the core app actually ships as plugins as well. So everybody here who has used Photoshop has used extensive plugins before. This is an interesting one, but what about Kubernetes CRDs? Yeah, probably some Kubernetes people in the crowd. Might not be what you think of when you think of plugin, but this is a way to take third-party code and third-party functions, integrate them over a well-defined interface, a data-driven interface, in with an orchestrator in a way that things can orchestrate across different data types. Largely meets our definition of plugin. Browser APIs, even broader. But yeah, browser APIs, same thing. You're using well-defined interfaces to put content into a host application, which in this case is a multi-tenant system for putting data onto a screen. Clippy. Anybody remember Clippy? Clippy is the perfect plugin. You're taking data out of an app like Microsoft Word, right? You're running some analysis on that. You're putting back suggestions, and you're putting pixels onto a screen to give a graphical depiction of those your suggestions. So this is all to say that this is a very flexible definition of plugins. But why don't we see these in games? And why don't we see these in 3D apps today? And I will posit this. Anything that does 3D, in games in particular, they need a GPU. And so lots of stuff happens on the GPU. Data is generated on the GPU. Data is resident on the GPU. And you don't want to necessarily pull that off to the CPU side in order to perform calculations on it for a plugin. So we need GPU-aware plugins in the future. So how do we solve this? Well, we have webgpu, which runs on a web browser. So this kind of gives you a multi-tenant GPU security model. This is a secure way in multiple tabs to isolate multiple origins and be able to generate 3D content and interact with the GPU, and maybe even run inference, in a safe way where you can't read data from other tabs on your system. Likewise, we have WebAssembly that is running in a web browser. And this is a true native sandbox. It's not Flash. It's not shelling out to system APIs. But we have this kind of model of WebGPU for GPU compute and Wasm for CPU compute. And in a browser, this integration works pretty well. You've got things like Emscripten for C++, Wasm Bindgen on the Rust side. There's more as well. These can communicate with these browser APIs over a JavaScript bridge. But outside of a browser, there's not really any way to do this in core Wasm. You've got F32s, F64s, i32s, i64s, and that's it. So obviously, most people in here have heard about the Wasm component model and all of the great things that have come along with that in the WASI space. And we think that this can solve this problem for GPUs. And so we would like to introduce wasi-gfx.
So wasi-gfx is a translation of the WebGPU spec into WIT, which is the language used to define components in the component model. And we need to extend that a little bit, because WebGPU by itself can't really draw to the screen. It relies on HTML canvas for that. That's where WASI surfaces come in. And that is completely window and graphics API agnostic, so it can run as a standalone window or as part of a larger app, or, as we're going to show later, as part of a game. And it can run a variety of graphics APIs like DX12, Vulkan, etc. And we have a reference host implementation of this. We call it wasi-gfx runtime. So if you're using Wasm time, you can just add wasi-gfx runtime, and that should give you all of wasi-gfx today. So let me show you a demo of this actually working. So Bevy.
Yep, that one.
Sorry. So Bevy is a game engine written in Rust, and it uses wgpu in the backend to actually draw the graphics. And wgpu internally uses actually webgpu. So that means we can compile that to Wasm into a component, and we can run a Bevy game inside Wasm time, if it's going to open. Do you think? Oh, no.
Oh, sorry, it rebuilt. I don't know why it rebuilt. But what you're going to see here is really cool, because we are going to be running an entire desktop-based game that is compiled to Wasm and running Wasm on the desktop.
Yep. So here you can see we can interact with the keyboard. So this is like a full Bevy game. Oh. What did I just do? No, don't want.
Full Bevy game, yeah.
I got to learn how to use computers. So how does WebGPU work on the web? So on the web, the way it displays anything to the screen, so its windowing system, is the HTML canvas element. And the HTML canvas element can be connected to a number of graphics APIs, like WebGL or webgpu. But there's only the canvas on the windowing side. In WASI, you want to be a little more robust. So we have WASI Surface, but in the future, it will probably be more powerful, maybe desktop-specific windowing systems, or maybe a specific app wants a more custom windowing API, and it wants to make sure that it can work with any graphics API, like we're starting here with webgpu. We also have WASI Frame Buffer, which is a CPU-based, just a frame buffer, so you can do CPU-based rendering. And in the future, there will probably be better, newer graphics APIs. So how do we make sure that any graphics API can work with any windowing system? That's where WASI Graphics Context comes in. And all WASI Graphics Context does, it takes the graphics API on one side, the windowing system on the other side, and the host is in charge of making sure that these two work nicely together.
All right, so what you saw there with the Bevy game, or what we attempted to show, was basically an entire application. If you think about that, there is still a host app that was loading the Wasm file, but is basically responsible just for putting Chrome around the window. And so for most plugins, you're going to want to be interoping with an existing graphics app, an existing rendering app. And so the way to do that, if you're just putting 2D data onto the canvas, is to hook the back buffer, which is relatively straightforward. So if you think about like UI, for example, you can think about little applets or little pieces of Chrome, different elements that composite onto a screen. You can just render those as subregions to the back buffer texture. We would recommend that you draw that using what we call a full screen quad pass. You actually composite that on the GPU. If you're just copying textures bit by bit, obviously you're going to destroy your transparency. You won't be able to do things like drop shadows or composite different layers of the UI. For 3D, things get a little bit more difficult. If you think about, like, I've got an entirely separate app that's running in Wasm here that's rendering 3D data into an existing application's canvas, you need to know a lot of information from the host app. Like if you're doing a deferred rendering context, for example, you might have 12 different render targets, and they've all got different parameters and different types of data and different channels they're writing out to. So the guest kind of has to be made aware of that, and it loses some of that abstraction from the host. And so an approach we found that works pretty well is rendering your own data in 3D, passing basic camera information over, basic matrices over to the Wasm guest, rendering into your own texture with alpha, and then just compositing that as a 2D texture onto the window. And so that, you can kind of control the, what aspects of you write to. You can still do things like screen space effects with different channels, but you can remain agnostic of the actual rendering environment for the host app itself. Another thing we'll show that works pretty well for certain use cases is actually letting the host app draw the data using its own shaders. If the data is of a known shape, known format, we can just put it onto the GPU from the guest, and we can have the host app, give it the same look and feel as all the content that's already rendered by the host game. See an example of this here. May the demo gods be on our side. All right, so here you see a map viewer. This is like something largely analogous to Google Maps, and you can see you've got kind of geospatial data, you've got elevation data, you've got textures that are like buildings projected onto this. What if we want to put 3D data into the scene? So we're going to load a plugin real quick that has just injected all of these little 3D buildings in the right spot onto the scene. And so this is all just a plugin based. It's able to communicate with the host, but it's shading it with the host's parameters, just like we saw before. So like all the lighting effects, like they look right. And you can see this is not just static data. This is 27 million triangles we're putting onto here. And even like we can interact with things like the angle of the sun to adjust the lighting on the buildings. We can do really dynamic calculations at runtime on the GPU that depend on data from the host in this Wasm guest. Pause that so I don't destroy my GPU with PowerPoint, of all things. OK, so how do we do that? How do we actually use wasi-gfx in a game? I'll say that wasi-gfx itself, it's a part of Wasi, open source. We have an open source runtime implementation we showed before. But it's much like a box of Lego parts. They're useful to build a model out of yourself, but to build a plugin runtime, which we at Renderlet are currently building, you need to be able to build logic for sharing host and guest resources. You need to be able to perform copies, manage state, be able to integrate with games, data models, 3D apps, etc. There are some challenges to make this work that we'd love to talk through how we solve them, and we're still in the process of solving. For example, most games are written in C++. Most of them are Windows apps. A lot of the Wasm ecosystem is a little bit more Rust-centric. Being able to map against different GPU APIs, even being able to get you that real-time 60 FPS performance. If you can't do that, you can't really work in a game. So how do we overcome some of these challenges? This is a perfect analogy for this. We've got two different puzzle pieces. We've got the game world. We've got the Wasm world. How do we plug these pieces in together?
So one hurdle is integrating C++ and Rust. So obviously, the plugins can be written in any language that compiles to Wasm and uses the component model. You can just make use of wasi-gfx and write a plugin in it. But for the host side, a lot of the wasi-gfx infrastructure and the Wasm infrastructure in general is written in Rust. So for example, wgpu, that's Rust. Wasm time is Rust. wasi-gfx runtime, that's Rust as well. Whereas the games, they're all written in C++. So how do you deal with that? So that's why we have to maintain a separate build tree where we generate a DLL with all the Rust artifacts inside. And we have to use a lot of FFI with cbindgen. We're probably going to move to CXX for better safety. And we end up with lots of wrapper Cs and void stars, which is not great, but we're working on reducing those. But the result is a clean C++ API wrapper around that low-level FFI function, FFI interface that we just ship a DLL with a nice C++ interface, and you can just make use of that in the game and feel like it feels just like regular C++.
What about performance? I'll say sometimes there's questions about Wasm performance. We say Wasm performance is pretty good. It's usually good enough for these kinds of use cases. Our benchmarks have shown that for heavily SIMD optimized code, like you'd often find for like matrix and geometry calculations in a game, we're at a P95 of about 80% of Wasm compared to native runtime performance. Most importantly, Wasm and really CPU performance for these kinds of modern rendering workloads shouldn't be the bottleneck. You need to be very careful with how you manage your resources so you can fully take advantage of the GPU. A mental model for this is using the CPU and using Wasm code, therefore, to configure the pipeline state that is necessary to get the GPU to actually build the rendering pipeline. So this is using things like GPU-driven rendering. We have like draw indirect with a count buffer, for example, has made its way into WebGPU in a preview in Chrome. This is a way to let the GPU take over and fully control the rendering process, reducing the burden on the CPU even further. What I was describing before about CPU readbacks is very important as well. Like if we've got data, like let's say we've got a texture, we've got a height map, we want to do some calculations, put a little mini map in a game. Super cool, right? The wrong way to do that is to take that, read it back to the CPU, put it into a buffer, map that buffer into Wasm, and have the guest code decide to perform some CPU-side calculations on it. The better way to do that is to have that mapped using everything Mendy described by wgpu into Wasm guest as a GPU-side texture, write a texture again, generate an indirect command buffer on the GPU, and let a compute shader go to town, being able to generate any kind of logic on top of that. Last, for generating data inside Wasm and putting it on the CPU, we're working on ways to map memory into the Wasm process so we can avoid those temporary allocations. So we're not like, for generating an image, we're not putting data and allocations in the Wasm address space. Ultimately, you should just have that end up copied into GPU memory. We want to be able to map that GPU accessible memory directly into Wasm as well.
So another hurdle is integrating DX12, which is how most games are, is the graphics API most games use, with webgpu. So our webgpu implementation in wasi-gfx runtime is based on wgpu. wgpu internally on Windows actually uses DX12. So what we need to do is get wgpu to be able to convert from wgpu resources into the underlying, get the underlying DX12 resources, and vice versa. If we have a DX12 resource, create a wgpu resource for that. That way we can pass it to the guest. And wgpu actually supports a lot of this on other backends already, so on Vulkan and Metal, it has support for most of this. It's a little bit lacking on DX12, so we're actively working on filling that gap. And this conversion is actually not needed, not necessary for the vast majority of resources. It's only the things that have to be passed between the guest and the host. For the most part, the guest is going to use its own textures and own buffers, and the same goes to the host. They're not going to mix and match too much. But the ones that they do have to go across the boundary, we're working on making sure that they can be converted easily.
OK, so how do we plug these puzzle pieces together? You need a surrounding wrapper, and this is what we were calling the renderlet plugin runtime. But this is a way to host Wasm components using Wasm time. It's a way to do all that DX12 mapping on the GPU. It's a way to automatically generate some of that graphics data yourself, so you can very easily slot this into a game, which we're going to see an example of right now. So we have taken something called Adria, which is an open source game engine. It's largely indicative of what you would find in a modern game engine architecture. Tile-based deferred rendering, uses mesh shaders, uses ultimate full bindless. It's a fully GPU-driven rendering pipeline, whereas a lot of graphic samples are just putting data, in a little Hello World app. Here, this was very, very hard to get all of the data integrated to, but it works.
Yeah, so as you can see, the top left, that's done in a plugin in a guest. And as I move the camera around, the guest is aware and is able to react to that. And same the opposite way. If I move things around on the guest, it can move the camera as well. You can see the background is black. We've got to fix that. But as you can see, there's two-way communication with the guest can set the camera position and be aware of if the camera moves. So that way, you have two-way data communication.
And it's a fully separate app, effectively, that's rendering into that existing 3D app over that defined data model. I got it. OK, so what do those kinds of data models look like for plugins? I'd like to give some heuristics on that. If you're building your own game, building your own kind of 3D app of any kind, what kind of data do you want to share with the plugin? There's no one-size-fits-all approach, but we'd recommend not exporting entire host app APIs. So if you're in C++ land, the example of this is headers. Don't just give plugins access to all of your headers, because you're probably injecting into weird places in your app that you've got state assumptions that you don't want to break through a multi-tenant kind of guest. Likewise, don't do the opposite of that and build very fine-grained, very bespoke mappings for single functions. I encourage you to think broadly about the world of things you can do with the plugin, and consider that when people are using your app like an SDK, they can build functions that you might not have even thought about yourself. So what we would recommend is using automatic mapping systems. If you have a documentation generator, for example, that's built against public APIs of specific subsystems, those are great candidates to put a lightweight layer on top of that can be exposed into plugins, and you can generate a lot of that binding code automatically. Likewise, use the concurrency model of the host app. Get yourself into trouble if you try to synchronize across different areas, if you try to introduce new concurrency primitives within different plugins, different guests. I'm not saying not to run plugins in parallel or anything like that. Just make sure that the areas they slot into your app respect the existing app's concurrency model as well. And then last, let's talk about restrictions, which is interesting because we're bringing the power of the webgpu API, entire GPU API to guests, to plugins. Why would you want to restrict that? Well, think about, from a host perspective, for restriction, what you want it to be able to do. Does this plugin need the full webgpu API? For example, would you like to just install a plugin into a game or into a web browser or anywhere on your system that's just mining Bitcoin with arbitrary compute shaders? Probably not. And so maybe for certain plugin use cases, you'd want to limit the ability to create new specific shaders. Maybe you want to use a set of pre-baked shaders. Maybe you want to have the host app allocate textures for you that then the guest can use. It can't reallocate, it can't generate new render targets, but it can render into existing data. There's all sorts of different use cases that you might want to think about locking down or opening up, depending on the model of the host app and the security concerns and the runtime concerns as well. For resource restriction, if you think about capability restriction, this is like a matrix of which of the APIs you can call and you can't call. Resource restriction would be what can I do with the data? For CPU time and Wasm time, we have something called Fuel. It does a decent job of effectively metering the CPU runtime of different functions. On a GPU, this is actually quite a bit more complicated because of how scheduling works within a GPU. There's not really a way to bound a running shader, for example, but you can bound like the size of indirect command buffers. You can do runtime queries for the performance of various things, and you can limit dispatches if things are taking too long. I would be curious if anybody has experience with kind of like limiting code on a GPU. Please come talk to us. For memory, specifically VRAM, particularly in console environments, you can be very constrained by these resources. Think about introducing per heap or more granularly, or for entire plugins, limits on how many resources, the size of the resources you can put on the GPU. This could be object count. This can also just be like raw heap size limitations. Sometimes even formats. Like sometimes you want to make things easy for your users. If you only support a certain type of render target, like if you only support HDR rendering, for example, maybe just restrict to that format, make it easy. But we think at Renderlet that plugins are the future, and we think that future is here. We think they promote content flexibility, reuse, all of that stuff we showed at the beginning, that back and forth process. Now, if we make our plugins data-driven, if we build like a plugin for glass breaking, and we connect it to data that animates it and parameterizes it, we've made our rendering safe. We've made it portable. We've made it fully data-driven and fully composable. All right, I think that's it. Thank you for your time. If you're interested in plugins, we'd love to chat. If you want to chat GPUs, chat WebAssembly, come talk to us. Yeah, and I think we have time for questions. If you have a question, we have a few of these very cool Renderlet hats we'd like to give out. So step right up. Thank you.
Hey, this is extraordinarily cool. Well done. I feel like you can't talk about producing games without a conversation about consoles. I'm curious about your experience, if you've had any, with porting wgpu or Wasm time to modern consoles.
Interesting question, yes. Without getting into specifics, I'm happy to have more of this conversation offline. Things port pretty easily to Xbox because it is basically just Windows. PS5 is a different story. We can have a conversation about that. That is not recorded.
Yeah, I have like 9 million more questions. I'll probably hit you up outside.
Perfect.
Thanks.
Hi, thank you for the talk. It was really interesting. I have actually two questions, principally about webgpu. So it's a long time that the community is not agree on absolutely everything. It's not stable yet. So I'm wondering how you can base something based on uncertainty, something like this. And the second one is about distributed computing. So unfortunately, on your terminal also Onyx runtime or something like this, so I expect you maybe played with compute shaders and stuff.
So,
yeah, Mendy, go
I
ahead.
think there were two questions there, right?
Yes.
One is about the stability of webgpu.
How can you base actually something like an abstraction on top of incertitude or something like this?
We're not stable either yet, so
okay.
At the time we're stable, they'll probably be stable as well. Do you want to take the other question?
Yeah, I mean, I would call webgpu stable enough for production work at this point. As of maybe like the last 6 months, it's still not. It's on in Chrome. It's still in trial in Firefox. They are working through some on the wgpu side of things, some integration issues still that are very like edge cases for the spec in order to get that fully enabled. But like the W3C spec for it, although it's like a living document, it is basically in its v1.0 form right now. So there's not going to be breaking changes, and future breaking changes are going to be probably put into new APIs within like new feature levels you could think of within webgpu itself. So yeah, like to Mendy's point, I think webgpu is more stable than wasi-webgpu at this point. But I think it is fully stable enough to build an application off of. But I do acknowledge that it has been a very long journey to get there. For distributed compute, I'm not sure if I entirely understood your question. Yes, like in general, like could you run this kind of stuff like wasi-gfx on a remote host and like pixel stream that back, or like run like compute shaders, for example, like if you're doing inference or something on a remote host and send the resources back? Absolutely. And I would say probably the #1 use case for webgpu today is probably compute shaders. So inference. So it makes sense, yeah. Did that answer your question, or do you have something more specific? OK, great. Thank you. OK, thank you so much, everyone.
Thank you.